Hello, everyone. In this video, we're going to look at part A of example 1 in section 4.2 and 4.3 on the Riemann sums and the definite integral. So in this section, we're going to learn about the strategy for computing area under the curve of a graph known as computing a Riemann sum. So let's get started with this example. So we're given, let f of x be a function e to the negative x squared. Part A asks us to use Leftsum and Rightsum with n equals 2 to estimate the area under f of x from x going to 0 to 2. So let's just unpack this statement a little bit. First of all, something very important to keep in mind is n equals 2. What does this mean? Well, conventionally, when we're computing a Riemann sum, we're given the number of rectangles we are going to use to compute the area. The number of rectangles is given by the n. So n is the number of rectangles used to estimate the sum, or rather the area. And the area we're computing is what's called a Riemann sum. All right, so we're going to use two different types of Riemann sums. We're going to use a left sum and a right sum. So the left and the right refer to which sides of the endpoints of a rectangle we use to estimate the area. So first, let's look at the left sum together. And again, we're computing an estimate for the area under the curve, under this function. So let's just sketch in what that area is. Well, that area is this area, if we were to paint it in, under the curve to the x-axis, and we're just going from 0 to 2. So this is the area we want to try to find an estimate for. Okay, so using a left sum and using two rectangles, we want to break up this interval from 0 to 2 into two chunks, two rectangles. So how we do that is break up the widths of our rectangles along 0, 1, and 2. We see with these chunks, we've created two rectangles. Well, two starts of rectangles. I haven't put the heights in yet. But this first part, we're looking for a left sum. So that means the height of the rectangle is going to occur at the left endpoint of my rectangle. So there would be my first rectangle. Now my second rectangle is going to be as high as the left endpoint. So that would be here. The left endpoint of this rectangle is that where the function hits our rectangle on that left end. All right, so here are our two rectangles that we're going to compute the areas of in order to find the left sum estimate. So what would that look like? All right, so let's call it something. We'll call this sum L sub 2, meaning left sum using two rectangles. Well, this is going to be equal to the area of the two rectangles we have drawn here. So the rectangle, a rectangle area, recall, is height times width. Height of this rectangle is the output value of my function on that left endpoint. So for us, that would be f of 0 times the width. The width of both of our rectangles is just 1. So f of 0 times 1 plus f of 1, which is the output of my function on the left endpoint of my next rectangle, times the width, which is 1. So now what is f of 0? We can use our function rule here. So we have e to the negative 0 squared times 1 plus e to the negative 1 squared times 1. And so for that, we get e to the 0 is just 1. So this whole term is just 1 plus e to the negative 1, squaring 1, just returns 1. And notice the negative is outside the square here. So just keep that in mind. We're squaring x and then we're negating. So we just get e to the negative 1 times 1, which is just 1. So if we put this in our calculator, we get a number about 1.368. So this, let's just recall, is the sum of the left sum rectangles. So this is the area of the left sum rectangles. And we're using this area of these two rectangles to approximate the actual area under the curve. And you might see that we're kind of doing not the greatest job here. A thought you might want to ask yourself is, how might we improve this estimate? All right. While you think about that, or after you've thought about that, let's look at the second part of this problem, where we are going to look at the right sum. So this is going to be very similar to what we just saw, except now, rather than split up our two rectangles at the left endpoints of our rectangles, we're going to use the right endpoints. So what I'd like you to do is pause the video and try to draw in those rectangles on your own, and then continue watching and we will compare our work. All right, so as you might have done, we are using the right endpoints of these intervals to create the height of our rectangles. So this first rectangle will have a height here on that right side, and this next rectangle will have a height way down here. So I'm going to just clean this up a little bit. So we have our two rectangles. Lovely, here they are. One rectangle, two rectangles. All right, so now let's go ahead and compute the right sum using two rectangles. So now we're using the right endpoints. So the height of our first rectangle could be evaluated here using f of 1 times a width of 1. Our rectangles still have a width of 1. Plus our second rectangle has a height of our function evaluated at 2 times a width of 1. So now this becomes, using our formula for our function, e to the negative 1 times 1 plus e to the negative 4 times 1. And I don't even need that times 1, right? All right, so we have e to the negative 1 plus e to the negative 4. So we can consult our calculator to get an estimate here. And we're getting that the area is about 0.386. So this is the area of the right sum rectangles. All right, so before we finish off this part, I want us to think about how these two estimates of the area under the curve compare and what they tell us about the area under the curve. So the main takeaway here that I want us to get or leave with is that the true area under the curve, I'll say the area under the curve, so not the estimate, but the actual area, is between these two estimates. So is between 1.368 and 0.386. And how do we know that? Well, first we can just observe that from the pictures. So in our left hand sum here, these rectangles over cover the area under the curve. They cover it and then more. The rectangles on the right hand sums are covering just part of the area under the curve. So we know that this first area that we computed in the left hand sum is an overestimate. And the right hand area we computed was an underestimate. And it's not always the case that left-hand sum will be over, right-hand sum will be under. It depends on the function. And you might want to draw some examples of other functions to see where or how you can determine what's an over or underestimate. All right, but we will leave this video at that. Thank you so much for your hard work. please feel free to rewatch, pause, go over this video again so this information is starting to feel comfortable. Keep up the hard work.